Hi there, welcome to this lecture series on matrix algebra. Today we have lecture 6. The topic of today is the inverse of a matrix. In this lecture we will cover the definition of the inverse of a matrix and some properties this inverse matrix would have. Okay, let's get started. Let's first recall the concept of an inverse in relation with a number. Let's say we have a number, we call it A, it's a real number. And then if there exists another letter B such that A times B equals 1, then this number B, which we know is just A to the power negative 1, is called the inverse of A. And now we wish to define a similar concept for a matrix. Now let capital A be a square matrix of size n. Then we say that another matrix B is the inverse of A, and we would write it such as B equals A to the power negative 1, if B has the following property. So A times B equals B times A equals 1, an identity matrix here. Okay. So we see that this B should also be a square matrix, n by n. And in this case, then, A is also the inverse of B because the definition is symmetric. Okay, just a note here, that is, an inverse can only be defined for a square matrix. If A is a square matrix of size m by n, then the inverse is of the same dimension. It's also m by n. Okay, let's take some example. Let's look at two matrices B, which is given like that. It's a 2 by 2. And then we have a matrix A, which is given by this. It's also 2 by 2. We claim that B is the inverse of A. And we can verify it by checking it directly with the definition. So we need to compute A times B, the product. So which is this A matrix here times this B matrix here. Okay, and then we just carry out the multiplication. So first row, first column cross, it's 2 minus 1, you get 1. And then you do first row, second column, so you get 2 minus 2, you get 0. And then second row, first column, negative 1, positive 1, 0. And then second row, second column, negative 1, positive 2, and 1. And we see that this is the identity matrix of size 2, so I2. And then one can also do the multiplication B times A by switching these two. And you can easily verify, I'm not going through the detailed steps, we are familiar with the product procedure, and you will see that you also get the identity matrix. Now, therefore, the definition is the conditions there are satisfied, and therefore B is the inverse of A. Now, one important thing for just any given square matrix, it might not have an inverse. We can take a quick example. Let's look at this matrix here, A, which is this 2, 1, 4, 2. And we claim that it has no inverse, and we're going to show it. So let's say it has an inverse, assuming, and the inverse matrix is 2 by 2, has element A, B, C, D. And let's try to find these A, B, C, D. So A times the inverse must equal to identity. which means this multiplication, if you carry out, the 4 elements there must be these 4. And therefore we can write out 4 equations. So the first one will be the first row, first column should add up to be 1. That I'll get 2a plus 1c shall be 1. That's this equation. Okay. And then this one cross that shall be 0. So I'll have 2b plus d must be 0. And then the third one is this one cross that. I'll get 4a plus 2c is 0. And the last one is this cross that. I'll get 4b plus 2d is 1. Okay. So we have 4 equations and 4 unknowns. And can we find a solution? Well, let's look. If I look at the first equation, 2a plus c is 1. And then I look at the third equation, 4a plus 2c is 0. So note that 4a plus 2c equals, you can take out a factor of 2, common factor, it's 2 times 2a plus c. Right? And if 2a plus c is 1, then this quantity equals 2. It should be 2, but according to the third equation, it has to be 0. Therefore, we have an inconsistent relation that is implied. So 2 does not equal to 0. Therefore, there is no solution. And then there are no solutions A, B, C, D that will satisfy this relation, and therefore there are no inverse matrix of A. So in that case, we would call that A is not invertible. Okay, so at this point, I should mention that this lecture for the rest of this would be quite proof heavy, in the sense that we'll be talking about all these properties of the inverse matrix, and we'll go through each of them and show how to prove it. Okay, so here I list 6 properties related to inverse matrices, and in the following of the lecture, the rest we will go through them one by one and talk about them. So the first one is and uniqueness of the inverse, and the second one, the inverse of the inverse, and the third one, inverse of scalar multiples, and the fourth one, inverse related with the transposed matrix, and then the fifth is inverse of a product, and then the sixth is called the cancellation property. Okay, so probably you can't just like bluntly remember all of these, and we will repeat each property and provide a proof for it. Okay, so let's continue. Okay, uniqueness of the inverse. So if the inverse exists, the right inverse and the left inverse of a matrix, and they are the same, which means if A times B equals identity, and then another matrix C times A equals identity, and here B is called the right inverse, and then C is the left inverse, if you shall distinguish them. Okay, and then this property says that actually B equals C. They are the same. Okay, so let's provide a proof. So we want to show that B equals C. So what we will do is we will start from B, and then using these 2 identities and some known properties, and then we will eventually reach C. Okay, so now let's start with B. And B, if I multiply B by the identity matrix, it doesn't change. So B equals I times B. And now the identity matrix I here can also be written as C times A, because that's what we assumed, right? Okay, so let's put here C times A times B. So this product is being performed first, and then you multiply by B. And then we use the property that for multiplications of matrices, if they line up in order like that, then performing this one first and performing that one first, they will give you the same result. So we can do A times B first and then multiply by C on the left afterwards. Okay, that's what we have here. And now, what is A times B? Well, A times B is identity matrix. So we get C times identity, and C times identity is just C. Okay, so we proved B equals C. Okay, so this further implies that every matrix commutes with its inverse. If A is the inverse of B, then the B is the inverse of A. The second property is about the inverse of the inverse. So if A is invertible, then A inverse is also invertible. Furthermore, the inverse of A inverse is A. So you invert it twice, you get yourself back. So certainly this property is true if A is a number. And let's see why it is also true for a matrix. Okay, so let's now denote the inverse of A inverse. We call that B. So the goal here is to show B equals A, right? So, and let's see if we can reach to that conclusion. So B is now the inverse of A inverse, which means B and A inverse, if you multiply them, you get identity. So let's put B on the right. A inverse times B now equals identity. So keep in mind, in the end, we want to show B equals A. Okay, so from this relation here, now we deduce. So we take this relation and we multiply on the left with the matrix A. Okay, so then I have A times the left-hand side here shall equal to A times the identity. Okay, so what is this product? Well, now we can play the same trick again. We can multiply the first two together and then the third. So this will be A times A inverse times B. And then the right-hand side, A times identity is just A. And now we use A times A inverse. A is invertible, and this product gives you identity. So you have identity times B equals A. And what is identity times B? Well, it's just B. So you get B equals A. And that's what we wanted to prove. Okay, now the third property is the inverse of a scalar multiple. So if A is invertible, of course, and then you have a constant C which is non-zero, then the scalar multiple C times A is also invertible, and the inverse of this is 1 over C times the inverse of A. Note that 1 over C is the inverse of C for a scalar number. Okay, let's make a proof. So what does this say is the inverse of CA is this, right? So we just need to show that this CA here times this, which is its inverse, will give me identity. Okay, so that's what we're going to prove. So now let's take this matrix and we put it here and multiply by that matrix we put here, and we want to reach identity. Okay, And then since it's a scalar multiple, this C here can be moved to another place. So I'll remove this bracket here, and then I move the C to the front. So I will have 1 over C times C. And then I'll have A inverse times A. So 1 over C times C is just 1. And then A inverse times A is identity. And I get identity at the end. Okay, and that completes the little proof. Property number 4 is about the inverse of the transposed matrix. So if A is invertible, then its transpose is also invertible. And the inverse of the transpose equals the transpose of the inverse. So the two operations, taking transpose, making inverse, you can switch the order and you still get the same thing. Now to construct a proof, now let's call this matrix here, right-hand side matrix, let's call this matrix B. So what we need to show is that the inverse of A transpose is B, which means A transpose times B shall be the identity. Okay, that's the aim of our proof. We want to show that, and that implies this property. Okay, so since we are doing transpose, and we will recall a transposition rule which we will use. The rule says the product of the transpose. If you have two matrices D and C, and you do the product of it and do the transpose, and it is equal to the transpose them first and then take the product, but in the reversed position. Okay, so this is D times C, and this will be C times D. Okay, now let's start from this expression on the left and to see if we can prove that it eventually equal to an identity. Okay, so A transpose times B equal to, what is B here? Well, B is this guy. We call that guy B, right? So I have A transpose times A inverse transpose. And now we use the transposition rule, which is written here, where the C will be my A and the D will be my A inverse. Okay, so then it becomes DC, which means A inverse A and transpose. And A inverse times A is identity. So I have identity transpose, which is still the identity because it's a symmetric matrix, the identity. Okay, and that is exactly we wish to prove. Now property 5, it's about inverse of a product. If A and B are both invertible, of course they are square matrices of the same size, and then the product A times B is also invertible. And it's the following. The inverse of A times B is the inverse of B times inverse of A. So this very much resembles the transpose of the product, where the transpose can be put on each of them, but then you have to switch the order. And the same thing happens to the inverse. Okay, so let's prove this. So we want to prove that this matrix here is the inverse of this matrix. And then we just need to multiply them and to show that you reach identity eventually. Okay, so that's what we put. A times B, that matrix here, times this matrix on the right hand side, and we want to show it becomes the identity. Okay, so we can remove the bracket with this multiplication, and then we can group these two in the middle to compute first. And then we see conveniently this is B times B inverse, which is the identity. So I get that. And then A times identity is just A. Then I have A times A inverse. And then that is just identity. So we complete the proof. Okay, so the last one is the cancellation property. It says that if A times B equal A times C, and the A matrix is invertible, then B must equal C. Okay, we can start with this assumption here, if A times B equal A times C, and using the fact that A is invertible, so we can have A inverse, which is also a square matrix, and then we will multiply on the left. So A times B, A times C, on the left I put A inverse and A inverse. And then A inverse times A is identity. A inverse times A is identity. I have identity times B equal identity times C, which is just B equals C. Okay? And now be a bit careful with the cancellation property. It does require the A matrix to be invertible. If it is not invertible, then the property would fail. Okay, let's take a quick example. So this is our infamous matrix A, which we have shown earlier that is not invertible. And let's take two matrices B and C. And let's see if I can verify that they satisfy the conditions in the property number 6. That is, A times B equals A times C, but B doesn't equal C. Okay, that's because A is not invertible. Okay, that is quick to verify A times B. We just carry out the product of the two matrices. If you work out the detail, you get this matrix 2 and 3, 4 and 6. And then we can carry out also A times C. That's my A and that's my C. It's a quick computation and you will get that. Look at these two matrices at the end and you see that they are the same. So A times B equal A times C, but clearly B does not equal C. And does it say that the property in 6 is false? No, because for the property 6 to be true, we want the A matrix to be invertible, and here A is not invertible. Let's talk about some indication of a matrix is not invertible. So first, make this observation. If there exists a non-zero vector, important, B should not be 0, such that A times B is 0, then the matrix A is not invertible. Now let's do a proof. We can prove by contradiction that we can assume the opposite of the conclusion and to see that if this leads to something that's absurd. Okay, so using the property A times B equals 0, and then we can multiply this by the A inverse, which is still 0, right? So 0 would equal to A inverse times A times B. And then this product here, we can multiply the first two first and do the third one. We can do A inverse times A and then multiply that by B. And then if A inverse exists, then A inverse times A is the identity. You will have identity times B, which is B. And then we see that B is a zero vector, which is a contradiction because we assumed that B is a non-zero vector. So we have a contradiction, which means the assumption we made here that A is invertible is false, and therefore A is not invertible. Finally, let's talk a little bit about how to compute the inverse. Just like very naively, how many operations will be needed to compute this inverse? Let's take a very straightforward, naive approach. So what will be the task? Task will be given a matrix A, n by n, with the elements A, I, J. I want to find another matrix, let's call it capital X, with its element x, j, k, such that capital A times capital X, this product here, gives me identity. I can write them out in detail. A times X will be this A matrix times this X matrix, and it should be identity. So we know the matrix product, and each element here would be the corresponding row cross the corresponding column, and you add them up, multiply element-wise, add them up, and you get that number. So I can write out any of them. So let's say I would take ith row here for A and the kth row in X, and then I will have this sum should equal to, it's either 1 or 0 depending on if it's on the diagonal or not. So if I equal k, it will be a diagonal element, so it must be 1, and otherwise it's not on the diagonal and it shall be 0. We'll have that, and for every element here. So we see that if the matrix A is size n by n, then I'll have n square elements in the identity. I will have n square equations for n square variables and all these x's. So we will have a huge system of linear equations, n square size. And if we apply our current method with the Gaussian elimination and the backward substitution, we know that that operation takes n to the third power, where the n is number of unknown. And then here the number of unknown is n square. So it's n square to the third power, which is n to the sixth power operation. So that is extremely time consuming. It would take a long time for the computer to carry out, or if you do it by hand, that will be terrible. So that is really not an efficient method. Fortunately, there are much better algorithms, and which we will cover in the next lecture. So we'll stop here with this comment that such a method is not good, and we're looking for better ones in the next lecture. Okay, so I hope you enjoyed this one, and I'll see you next time.